In this video, I wanted to explain how to derive the charging equation for an RC circuit. So this is done by first utilizing the loop law, or Kirchhoff's loop law. So basically what the law states is that around any closed loop, which is connected by a source of voltage or a source of electromotive force, the sum of the voltages will add up to zero. So the way that we apply this law is we can create an equation. So our electromotive force is given by this E. So, and we recall our capacitor equations, Q equals CV. So the voltage dropped over the capacitor is Q over C. And this will all add up to zero because, again, by the loop law, everything going around this circuit is eventually going to go from high to low, and everything will sum to zero. So from here, we essentially substitute dq dt for I because the current is also defined as dq dt. So this is one of our key equations. Now that we've got the equation in this form, what we're going to do is solve the differential equation. And if you remember from calculus, differential equations are equations that involve differentials, which are such as dq and dt. And the way you do this is by a technique called separation of variables. And what this means is we're going to separate dq and combine it with all the q's in our equation, and separate dt and combine it with all the t's. We don't have any t's, so it'll just be with some constants. And once we separate them on opposite sides of the equal sign, we're going to take the integral, and that will allow us to solve our differential equation. And just to reiterate what a differential equation is, essentially what a differential equation is it's the equation of the slope of a certain value. So we're solving for the charge. We want to find the equation that'll give us the total charge within the circuit. And the way we do this is we need to do our differential equation because of our I here, which is defined using dq dt. And what that does for us is we get an equation that gives us the slope of q versus t graph, the instantaneous slope, which is the derivative, and then based on that, we're able to separate these two variables and get a particular solution, which will be our charge. So continuing back to solving the problem, the first step that we need to do is remember to multiply by r. The first step we need to do is move all our differentials to one side. Now we're going to divide all sides of the equation by r so that we can isolate our differentials. Once we do that, We're now going to combine this into one expression by finding a common denominator. Now we are ready to utilize separation of variables. And one more step, we are going to be getting, dividing both sides of the equation by this and by this. Now we are ready to take the integral of both sides. And it's going to be a definite integral because we're going to be going from 0 to t for our time, because t is just our time. And here we're going to be going from 0 to q as a function of t. Now, before we take the integral, I wanted to multiply both sides of the equation by -1. What this allows us to do is we get rid of the negative sign that we can see that our integral is going to have, because this is in the form of ln of u. And we're subtracting x here, so we're going to have a negative sign. Something, for example, let me illustrate this with an example. Let's say we had 1 over 1 minus x. So if we were finding the antiderivative, we would do ln of 1 minus x. But we don't need to do that here because we can multiply both sides of the equation by -1, so we get a cleaner answer of x minus 1, which will allow us to more easily compute our particular solution because we won't have to multiply by -1 at the end when we expand. So essentially, that's why we have to multiply both sides of the equation by -1. We don't have to do so at this stage, but since we can foresee that our answer is going to involve a natural log, it makes sense for us to multiply by -1 so that our answer can have a clean variable instead of having a negative sign in front of the variable. So I'm just going to add that negative sign right there. And continue. So from here, we're just going to be doing some smooth integration. So what can get tricky here is remembering which are constants and which are not. So in our equation here, R and C are both constants, so they just get pulled right out of the equation. Same with electromotive force and C. Again, these are both constants. But what's not a constant is our Q. So we need to be finding the antiderivative based on the form of this equation. And we can see that the form of this equation is in a natural log. So what we'll get is something that looks like this, going from 0 to qt. And here, antiderivative of a constant is just t, and we're going from 0 to t, and this is the only thing, because if we plug in 0, we would just get 0. So now we can clean this up and solve for q. So in order to solve for q, basically, we need to plug in and we're plugging in 0 for q. Remember, q was our variable of integration. The rest are constants. So 0 minus EC, so we get negative EC. Okay, and on this side, we just have T over RC. Next, we are going to rewrite this again into a single equation. Yep, and now this is the stage where we can actually um, expand and solve for what's inside the parentheses here for q. So this is what that looks like. ln is just not log base e of something. That's what ln means, just a refresher. So we're going to raise e to the negative t over rc. That's going to be equal to everything in here. Now, pretty much smooth sailing from here. We just have to basically just simplify this. So multiply both sides by electromotive force times c. Isolate our variable q, which, reminder, that's what we're solving for. And you might have noticed that I dropped writing q of t. Q is still a function of t. It just is more cleaner in the context of the equation to just write q, which is why we dropped writing our q of t. So now, very last step, we just have to factor out that, and this is the general form for our charging equation. So we got our general form. So just to recap, what we did was first we quickly analyzed our circuit. It's an RC circuit because we have a one resistor and one capacitor and one battery, of course. And based on that, we were able to use Kirchhoff's loop law, and essentially we made sure that everything inside of the loop added up to zero, all sources of voltage, um, all sources and loads, add the sources and the loads together and you get zero. And then once we did that, we replaced I with dq dt because that's the definition of our current, which is charge per time. And after we did that, we were able to use separable equations, or the technique of separable variables, in order to solve our differential equation. And we went through our solution for our differential equation, did some calculus, and we ended with our final answer, which is the charge inside the circuit is given by the electromotive force times the capacitance, and then times 1 minus E times negative TRC. Now, a couple of things I wanted to mention before ending this video was the charging curve for what this looks like. So I'm just going to show that real quick. So if you'll notice, if we graph Q versus T, it's going to look something like this. Or let me draw that better. Our asymptote is going to be at E times C. So basically, the charge is going to always approach E times C, but never quite reach it, but at time equals infinity, we assume that the charge inside is E times C. And this actually makes sense because if you think about it, back to a circuit here, when the capacitor is discharged, what's going on is that it acts kind of as a short circuit, so it acts as just a regular wire. But as time reaches or approaches infinity, what's going to happen to our circuit is this is going to create an open circuit, and our capacitor will then be fully charged. And its value is going to be, or the voltage that it stores is going to be equal to, um, sorry, the charge that it stores is going to be equal to CV. And remember, our voltage source here is our electromotive force. So that's what we will be approaching as time goes to infinity. So thank you for watching, and leave any suggestions or comments or questions, comments, questions, or concerns in the comments. Thank you.